Hi, everybody, and welcome. Happy to see you all here. Today, Mats Nilsson will talk about the land-atmosphere exchange of greenhouse gases or boreal ecosystems under climate change. And he will talk about this in this internal seminar series, Värt att veta, that we have every second Wednesday. And this internal seminar series is a way to get the department seminars to go more public in this public area where we can meet together. And we hope that in the end of this seminar that you will stay and discuss a bit with Mats about what he has talked about. And after Mats has had his seminar, I will ask if there are any questions, and then I will go with this microphone, and you can ask the question in the microphone, so we get it with the broadcasting or that we also do. So it's important that you talk in the microphone. I hope you have found fika. It's over there. And I will also say that the next seminar in 2 weeks will be held by Frauke Ecke, and I hope to see you here then too. We are also planning a more external seminar series during spring, but they will be, as they always have been, in Swedish, because then we will also reach out to people outside SLU. But this is in English, and I would like Mats Nilsson to come up and start.
So, thank you very much. So, this presentation, I'm going to present ongoing research, which is a common effort of a lot of colleagues, and also based very much on help from research technicians and students. So the overall outline is some of the background, the concepts behind the biosphere-atmosphere interactions. Then something about the study approaches, the measurements, measurement techniques. And then something about research infrastructure, which is called ICOS, which stands for Integrated Carbon Observatory System. And then some examples of different research questions that we have addressed. So to start with the background, so this is one way to view it, that we have the atmosphere and the properties of the atmosphere when it comes to radiative forcing is determined by the content of greenhouse gases, the surface energy fluxes, and water exchange. So all these three groups of properties or processes together determine the radiative forcing, which is commonly known as the greenhouse effect. And those properties then determine the climate settings and the weather conditions. For example, both range and seasonal distribution of, for example, temperature and precipitation. And then the climate settings and weather conditions then determine the biome distribution or the geographic distribution of ecosystems over the world, and also process rates. For example, process rates of uptake or release of what we call greenhouse gases, for example, carbon dioxide, methane, and N2. And those processes then directly influence back to the atmosphere. So here we have an interaction, and this is the way it always have been. So processes in the biosphere have always interacted with the atmosphere, and thereby, to a very large extent, also determined the properties of the atmosphere. What has happened then more recently, which in this case is, say, the last 200 years, is that due to human activities, we have added greenhouse gases to the atmosphere, mostly but not only carbon dioxide from the burning of fossil fuel, and also to some extent from land use change. And this continuous addition of greenhouse gases to the atmosphere then influences the composition here of greenhouse gases in the atmosphere, which then in turn may influence the climate settings and weather conditions. So much of the research we are involved in can be illustrated by the red question marks here. So it's about how the climate settings and weather conditions influence ecosystem processes that are directly linked to uptake or release of greenhouse gases, carbon dioxide, methane, or N2, and then how the ecosystems interact with the atmosphere, with either releasing greenhouse gases or increasing the release of greenhouse gases to the atmosphere, or removing greenhouse gases from the atmosphere. So most of you probably all have seen this famous time series over carbon dioxide concentration in the atmosphere. Normally one focus on the increasing trend. I would say that much of what we are working on is more connected to the seasonal variation in CO2 concentrations that you see in the time series. And it's even much more pronounced if we look at the time series from higher latitude. This is from Alaska, Point Barrow. And even if you see a steady trend in increase in the concentration, you also see that we have a substantial seasonal variation in carbon dioxide. And this seasonal variation is approximately 10 or even more times higher than the average annual increase. And this seasonal variation comes from biological processes, and it's due to mostly or entirely determined by processes in terrestrial ecosystems, and very much of it from the northern hemisphere. So terrestrial ecosystem processes at the northern hemisphere. I just want you to focus on this red area, or area enclosed in this red circle here. I mean, this cartoon is based on thousands of scientific papers and showing our current understanding of carbon stores and fluxes globally. But this red enclosement here illustrates the terrestrial fluxes, the uptake from photosynthesis and the release from respiration. And each of these fluxes is more than 10 times as large as is the annual release of CO2 to the atmosphere from anthropogenic processes. So the natural processes are so large, so even small perturbations of the uptake, which is the photosynthesis, or the release from respiration, can easily influence the rate, both the seasonal variation in CO2 concentrations in the atmosphere, but also influence the increasing trend of the concentrations in the atmosphere. So this is very much the background or the framework in which we are working. And our work is focused particularly on understanding the carbon and greenhouse gas balance of the boreal biome. We are not working only on the boreal biome, but much of what we are doing is focused on the boreal system. So, and most, but not only, but most of the studies I'm presenting here are based on long-term field studies. And and we approach our studies from different angles. So one important part is a measurement technique called Eddy covariance measurement, which measure exchange of, for example, carbon dioxide, methane, other greenhouse gases, exchange of energy or water at the ecosystem level scale. We also use chambers, both manual chambers and automatic chambers, at the plot scale for much more detailed analysis. And we use long-term monitoring approaches as well as field manipulations to understand how various properties or external factors affect the exchange of these gases between the biome and the atmosphere. So just a few words on the Eddy covariance approach. It's based on mainly measuring two different things at the same time. And we can say that the important thing here is to measure at quite high temporal frequency, which is 10 to 20 times per second. So what we need to measure is the wind movement in all three directions to be able to calculate the vertical movement of the wind. And at the same time, and as more or less at exactly the same point in space, we're also measuring what we're interested in, for example, carbon dioxide or methane or whatever it is. Also at the same frequency, so 10 to 20 times per second. And then more or less you can multiply the vertical movement of the air mass with the concentration, and by that deriving the vertical flux of carbon dioxide, energy, water, or whatever you're interested in. And this kind of measurement technique has today become a standard technique globally, more or less. There are other approaches as well, but it has become quite important tool. And so you can think, if you think of the ecosystem as a box, and inside this box there are a lot of processes going on. We have photosynthesis of both trees and other plants. We have respiration processes from the living plants and from degradation of organic material, and one can divide that at different scales. But with this Eddy covariance method, what we are measuring actually, that's the exchange between this box, the ecosystem, and the atmosphere. It's indicated here by the red circle enclosing the two arrows. And one need to keep in mind that what we are measuring is a net flux, either a flux of something from the atmosphere into the ecosystem, or from the ecosystem out to the atmosphere. But whatever direction we have of the flux, we have always processes going on that act in both directions. So we have photosynthesis taking up carbon dioxide, and we have respiration processes releases carbon dioxide. So what we actually are measuring is just the net between these two fluxes all the time. Then we have tools, actually models, that enable us to derive the photosynthesis and respiration respectively. So this is the major approach on this ecosystem level measurements. And then we need to do a lot of other measurements to understand the different processes within the ecosystem. So from those Eddy covariance measurements that are conducted at the frequency of 10 to 20 hertz, today it has become more or less standard to average those values over half hour. So what we see here is the half-hourly values. And the notation is such that positive values means that we release something to the atmosphere, and negative values means that we have uptake from the atmosphere into the ecosystem. So positive values means that respiration dominates over photosynthesis, and negative values means that photosynthesis dominates over respiration. It's not either or. Both processes very often occur at the same time. So this is a diurnal pattern that we see here. And then those numbers can be summed to daily values, as illustrated here. So we have the number of days on the x-axis, and we have the daily fluxes here, indicating that we have release during winter time, and we have release during autumn and early winter time, and we have uptake during summertime. Those daily values can then also be summarized to derive what we say a summation curve, a cumulative curve for a year. And then in this case we start from the 1st of January and then just add the numbers. So what that curve indicates is that during the first 3-4 months we have only respiration, or that at least respiration dominates, leading to a net loss to the atmosphere. Then in spring, early summer, when the photosynthesis kicks in and it starts to dominate, we have a net uptake, which is indicated with the line going downwards. And then in late summer or early autumn, the respiration processes starts to dominate over photosynthesis. And then the final number at the last of December indicates the annual balance. And in this particular case, shown in the graph here, means that we are back to zero. So this particular year and this ecosystem balance for that year was zero. So neither a net uptake nor a net release. So these kind of measurements have for very long been conducted based on short-term research projects and run by research groups all over the world. And since more than 10 years back in Europe and approximately the same time period in US, there have been activities to try to get those short-term research project-based activities into something more long-term. So in Europe, we have established something with a short, or the acronym ICOS, which stands for Integrated Carbon Observatory System, which is a research infrastructure. And there are similar in US, and there are other still more loose networks in other parts of the world. But all of those attempts aims to have more accurate and more long-term stable measurements of all kind of exchange of all kind of fluxes between the globe and the atmosphere. So greenhouse gases, direct energy, water. And currently ICOS is including 12 different countries and around 100 measurement stations. And there are 3 types of measurement stations. So there are measurements over the ocean. There are what we call ecosystem measurements, or ecosystem stations, which measures the direct flux between an ecosystem, for example a forest, and the atmosphere. And there are what we call atmospheric measurements that measure concentration up in the atmosphere at about 100 to 150 meters height. And those numbers then have more regional representation. And together with atmospheric measurements at several points, then we can derive flux patterns or exchange patterns over more continental scale. And so this infrastructure is based on the measurement stations, ecosystem station, atmospheric station, and oceanic stations. And then data is uploaded more or less on a daily basis from all those stations till central facilities. And then data is processed and quality checked and then deliver it to something which is called the ICOS carbon portal, which physically is located in Lund in Sweden. And then at this carbon portal, all this data are freely available for anyone, any researchers that are interested to use the data for different research activities. And both raw data, or more or less raw data, is available, but also a lot of different products to be able to see what the exchange patterns of entire Europe looks like, and how it's connected to different processes, and so on. So then, turning over from this to some examples. So long before ICOS, we started to measure exchange of carbon dioxide on mires. And we have worked on a mire 60-70 kilometers away from here, within the Vinden experimental forest, mire called Deger Stormyr. We started 2001. So here is data from 12 years, between 2001 and 2012. And this graph is built the same way as the earlier graphs. So every year starts 1st of January, and then we just sum the fluxes we measure. So with this, the data from these 12 years illustrate is that you, from 1st of January until April, May something, the mire represent carbon release to the atmosphere. And then from late spring, early summer, photosynthesis starts to dominate and take up carbon dioxide from the atmosphere through photosynthesis. And then in late summer and early autumn, photosynthesis is still ongoing, but then the respiration processes has become larger than the photosynthesis. So then we start to have a loss back to the atmosphere. But as you see, for these 12 years, all years, the mire represent a net uptake from the atmosphere. And the annual uptake is more or less exactly the same as the long-term average over the last 10,000 years. I mean, I can say that because we can compare with data derived from peat coring or coring mires. So we know it's around 20-30 grams per square meter per year. That's the average over the last 10,000 years, and that's the current average as well. When we started with this research 2001, then there were a number of papers out claiming that the mires were about to dry out and all carbon in the mires were expected to go up to the atmosphere. So then one talked about the carbon bomb from the mires. And I would say for mires in the boreal region, this is probably not true. If we go into temperate areas, southern Europe or Central Europe, for example, there the mires are on their southern borders, that might be different. But for the majority of peatlands, which you have in the boreal and subarctic region, I really doubt that they are threatened by climate change, as it is at the moment at least. And then another example based on measurement at one of our ICOS stations, which is a forest station, a tower in a forest at Svartberget, close to Vinden, 60 kilometers away from here. So, and this cartoon then just illustrates the tower, which is equipped with a lot of different instruments. So we measured both concentrations at a lot of different levels, up to 150 meters. And we're also measuring direct fluxes with this Eddy covariance technique. And for the example I'm presenting here, we are looking at the measurements from 80 or 85 meters height, which represent the entire boreal landscape, not just one specific stand, but quite a large area. So this illustrates, in this map here, the red star illustrates the position of the measurement equipment. And the white lines here illustrate the source area from where, depending on where the wind come from, we are measuring within these lines, and these the different lines here represent if it's 50% or 60 or 70 or up to 90% of all fluxes coming into this area. And within this landscape over which we are measuring, then we have different landscape elements. So forests dominate with close to 80%, then we have marshes 12%, we have clear-cut areas, we have some agricultural land, and we have some lakes. So if then, and in this case we have measured not at all from 2000, but during a much shorter time period. So here we have data from 2 years. But from those 2 years, 2016 and 17, this landscape represent a net uptake. So but this is not just forest. So this is the mix of the result from the processes in the forest, marshes, agricultural land, and lakes. But it is a net uptake not so far away from the average boreal forest uptake. And here just an illustration of that one can partition this net ecosystem exchange, the net flux, into the component fluxes. The GPP based on the photosynthesis, or which is representing the photosynthesis, and the respiration representing both respiration of plants and respiration from degradation of organic material. So then moving to just okay. So then before ending, moving into the processes of this summer, we have extreme weather this summer with a drought. So were we able to capture the effects of this drought? So what I present here is data from the different Swedish ICO stations. So here we have a station in southern Sweden, spruce forest, pine forest north of Uppsala, and here we have a mixed coniferous forest outside Vinden, close to Umeå. And if we look at the southernmost side, there we see a very clear signal where the uptake has been substantially hampered by the drought. We see no much effect at all at the pine forest outside Uppsala. We see an effect, not very strong though, in the mixed coniferous forest in Västerbotten. If we then move to other ecosystem, both to an agricultural soil in Västergötland, there we see a substantial effect of the drought, resulting in much less uptake. If we look at the Maya ecosystem, close to Umeå, data from the same Maya as I presented earlier. As I said earlier, over all early years, the Maya has always represented a net uptake. But if we look here for this year, 2018, it has already passed the zero line. So this year will be the first ever, since we started measure at least, then the Maya will represent a net loss to the atmosphere. The data we have here is until last Thursday or Friday. So it's very recent. So you see the other years here is the Maya represent a net uptake. But the drought this year turned the Maya into a net loss. And finally, we also had forest fires this summer. And if we look at the data from the high towers, we should be, or at least potentially be able to see the signal from the forest fires. If we look at the CO2, this red circle represents approximate time period where we had the forest fires. If we look at the CO2, it's very hard to distinguish any signal from forest fires. That's very much due to that there are so many other processes. that involve CO2, so it's hard to distinguish. But we're also measuring, for example, Cu, carbon dioxide, which is known to be a good signal both for fossil fuel and biomass burning. And here we see a clear increase during this time period. Methane is also known to be a marker for fossil fuel burning, as well as biomass burning. And you see here, even if data is scarce, we had a lightning strike in the same time period, so we lost nearly all data during the forest fire period. But we have some time periods clearly indicating very high concentrations of methane. So we can use the data on the concentration of methane and CO to actually derive how much of the CO2 we see at this time that actually come from the forest fire. So this is just another example how the data can be used. Okay, so just finally then, that all ICOS data, as I said earlier, is freely available, as is also the physical infrastructures, the measurement stations. We want all researchers that are addressing and working with research questions that can in any way benefit from these physical research infrastructures also. Thanks.
Thank you, Mats. So then we open up for questions. Do you have any questions? I have one question, so I can take that question while you're thinking about your questions. So do you know how the data is used? This is used in Sweden, EU, from the ICOS stations. Researchers use it, but do Naturvårdsverket, the government?
If we start with Sweden, so far data from ICOS and pre-ICOS time is not very much used by the non-academic community. So governmental organizations or political organizations are utilizing it very limited so far. And it's kind of similar at the European level, even if there it's used to larger extent. And that's very much due to this, to the carbon portal, the common facility, which are composing products delivered for the European country and the European community.
Okay.
But that's one very important ambition, both within the contributing nations, but also within EU, to really provide data and information to the society.
It seems to be a lot of interesting data, but maybe it's hard to interpret them. You need someone that is more familiar with the data and how with the systems.
Yeah, that's right. But that's also one of the main objectives with this data portal. I mean, at the data portal, you can find both more or less raw data, but also products that have processed the data at different levels and to the levels, so it could be used and understood by more or less anyone, not requiring any in-depth understanding of natural science.
Any questions? Good.
Hey Mats, yes, you were saying that you didn't think that climate change would affect the Meyer system at the northern hemisphere, but the results from Svartmyran, I think, show that the drought this summer made them a carbon source.
Yes, that's right. The thing is, if we look at both measurement and predictions, both the weather combinations, it differs slightly around the globe. But for much of the boreal area, both measurements and predictions are such that it will become actually more humid. I mean, one thing is that we have a temperature. That's one reason to why I'm very hesitant to use the word global warming, even if I fully understand why it's commonly used. I prefer to express it that what happens when we increase the radiative forcing in the atmosphere, that we capture more energy in the atmosphere. Then this energy can be used for different or used for different purposes, either increase the temperature or evaporate water. So one result is that we have more water in the atmosphere also, and evaporating more water will result in more precipitation. So the water needs to fall down somewhere. And in much, not all of the entire northern hemisphere will see more precip, but if we take Scandinavia and Western Eurasia, there the predictions are that we'll actually have more precip, especially during the summertime. So that's also one background why I'm really hesitant to, if we really will turn the systems into a net sink or net source instead of a sink. But I mean, you're actually absolutely right. This kind of event we had this summer, that definitely turned it into a source. It did.
Someone else that has a question? Good.
Hi, thank you for a very nice presentation. So I was wondering about your fire results. So as I see it, you can only pick up the fire during the fire itself, right? And then after that, the system bounces back to its original state very quickly. So wouldn't you argue that based on that, fire has a limited effect on the atmospheric exchange?
Yes, most likely, but yeah, it's no, not really. I mean, the thing is that you have the atmosphere with a very large capacity. So even if we have a very large amount of carbon released during a forest fire, in this case, I mean, this is just more or less raw data. So we haven't been able yet to really process the data and try to estimate how much carbon that has been released. But so even if it's a large amount, the total capacity in the atmosphere is such, so you need really huge forest fires to really influence the absolute amount of carbon in the atmosphere. And yeah, okay, then the answer on your question is more or less, you're right, the effect in the atmosphere is quite limited, definitely, on the global scale, yes. Even if we thought of the forest fire in Sweden as a very large fire compared then to fires in, for example, Canada and the southern hemisphere, this was a small one. All the forest fires here together were small ones. Yeah.
Good. Some more questions? Good.
I'm wondering if the data could be used, or if it is used to compare different types of forests, and what like the effects of production forest versus natural forests and things like that.
Yes, I mean the data. I mean, as I presented here, I presented mostly as measuring and generating data then from this measurements point, and then one can say, okay, you are measuring. Even if we have a number of many more sites than are included in this ICOS in the research infrastructure, if we have in Sweden, I don't know, 40, 50 sites with a covariance, and we say we have quite a number of measurement sites, but still one can say it's very limited. You are measuring quite small areas, and that's true. But these numbers, more than just being used to estimate the fluxes of a certain time period and at a specific location, data is also used to parameterize modos. So yes, we are measuring at forests of different ages, different species composition, and as you say, more kind of natural forest, whatever that is, and more production forest. And then together with models estimating then what is the functioning or the fluxes from these different forest types.
Have you seen any like results of that? Can you?
I cannot. I have seen a lot of results from different forests, but it's not so that I can give a general overview. I mean, there are no. I
Not yet.
don't have that kind of overview. Actually, there are ongoing activities in Sweden. Both much is over production forest. There are a few measurement sites of more kind of old growth forest. There are one site outside Uppsala, one between close to Arjeplog, north from here, and so and. Those two forests, old growth, they are relatively close to zero, close to balance. They are more or less a net uptake, but very close to zero. So then it depends very much on year as well. Some years you may have a net release. Whether that's a general pattern or not, I would leave that for now. But there are an intense scientific debate about if old forests are actually losing carbon or if they still are taking up. There are papers pointing in all directions.
Thank you.
So next talk from you will be about that, or?
Yes.
Good. It will be interesting. So, any more questions? Good.
I was wondering if this includes only the forests or also the agricultural land, because there is huge agricultural land which also should be considered.
Yes, there are. If we take in Europe, for example, there are measurements going on. I would say for all kind of systems, all kind of ecosystems. Also, not just ecosystem. We are including urban areas as well. So there are measurements going in both large cities and small municipalities. But there are a lot of measurements going on in agricultural land as well. And as you say, it's very important, or as important as other forests. So yes.
Okay, I lost track of time, so I don't know if we have any more time. But is there a small question that needs to be asked? Yes, of course.
He asked me to be nice here. I'm just wondering about, I mean, from the European perspective, is there ecosystems that have become net sources of, for instance, CO2 for a longer period of time, and what are the processes behind those?
Sorry, what did you say?
If there are ecosystems at the European level that have become net sources of CO2 or methane since you started, or ICOS started the measurements?
Not that I'm aware of that we really have had a transition from one state being a net uptake into another state. No, but depending on ecosystem, it might be so that in some cases they are much more dynamic also over a multi-year time scale. So some years uptake and some. So it depends on how sensitive the system is to the weather conditions. But I'm not aware of any transition that we really have moved from being a net source or net sink to becoming the opposite. No.
Okay, then I think we have to thank Mats for an excellent talk. And before you clap your hands, I would like to say that Mats will stay here for several minutes, for the whole afternoon, for a couple of minutes. So if you are interested in discussing this very interesting data set and how it's used and can be used, then please do that. So thank you, Mats.